So today we're going to continue talking about magnetism, and before too long I'll tell you how to pronounce this thing, which is a mouthful. Last time there was a whole bunch of slides at the end about magnetic torque and electric motors, things like that. Even in non-pandemic years, I often don't get a chance to go over those slides. So I wanted to give you the briefest of brief overviews of what's on those slides before we get into this. So one of the things that's discussed is a wire loop that is in a magnetic field. So this is a coil of wire. I mean, there's not a battery on this thing, but you could easily imagine that there would be one, and that battery might be driving current around the thing like this. And what's important is that last time we talked about how the magnetic force is F equals QVB sine theta, where theta is the angle between the magnetic field and the velocity. So here, for example, the current is to the left, which means that the electrons are moving this way. And so the angle between the velocity of the electrons and the magnetic field is 0. Sine of 0 is 0, and so the magnetic force here would be 0. Now up here, the current is this way, which means the electrons are going that way, which means the angle between the velocity of the electrons and the magnetic field is 180 degrees. Sine of 180 is also 0, and so the magnetic force here is going to be 0. However, over here, remember that the magnetic force is largest when the velocity and the magnetic field are perpendicular to each other. So in this case, the electrons are down, the magnetic field is this way, which means that V cross B is out of the page, but because it's electrons, the force is QV cross B. Q is negative, that means that the force is actually into the page. And so you would find a force that's into the page with a magnitude of B0 times the current times the length of this side. As I said, the force up here is 0 because it's anti-parallel to the magnetic field. Over here, so now the electrons are going this way. The magnetic field is like this, which means that V cross B is into the page, meaning QV cross B is out of the page, which means the force is going to be out of the page. And then, as I said originally, the force here is 0. So what's interesting is that this is going to push it into the page, this is going to push it out of the page. At the end of the day, you're going to find that this thing starts rotating, or at least wants to rotate around. So in other words, you're going to find that there's a net torque on this loop, and indeed this is how electric motors work. There's some magnetic field, there's a coil. This is, the axle of my 2015 Nissan Leaf, and this is what makes it want to move very fast and accelerate. So so we can calculate the torque here. Now remember from physics 1250, there's a sine theta with the torque, which is sort of there to make sure that the maximum torque is when the force is at 90 degrees from the lever arm. So the lever arm here is basically half the length of this loop here, as we'll talk about in a second. Because the force is out of the page, that means indeed the force is 90 degrees to sort of the rotation axis. And so sine of 90 is 1, sine of 90 is 1. So that sine function is going to go away. Again, there's two sources of torque here. Now the torque does not cancel each other out because this is into the page, this is out of the page, but they're both causing the thing to want to rotate in a particular direction. So these things don't actually cancel each other out, which is kind of like, when you're trying to get a nut off of your tire. You're pushing down here. You're pushing down here on the tire iron. You're pushing up with your other hand. Those torques add together. They don't cancel each other out, even though one is down, the other one is up. Same thing happens here. And so you end up getting this for the torque that's on this coil. And what's interesting about all this is that if you stare at this long enough, the easy part is that this is the same thing, so you end up with twice that. But if you stare at this long enough, you realize that twice delta x times L, that's actually just the area of this square. And so you find that the torque is the area of the loop times the ambient magnetic field times the current. And that makes a lot of sense because the bigger the loop, the more the torque. That makes sense. So for example, like the bigger the electric motor, the more torque you're going to get out of it. The more current you pump through this loop, the more torque you're going to get out of it, which makes a lot of sense, right? In my Nissan Leaf, when I put my foot on the pedal, it puts as much current through this thing as it can do. And then there's the ambient magnetic field. Now typically this ambient magnetic field would be from, say, a permanent magnet. If you out there listening have a clever idea to making permanent magnets more powerful, hold on to the idea and patent it, because you can make every electric motor in the world more efficient if you can just manage to increase this magnetic field. So that's the lesson, is that the torque is related to the area and the magnetic field and the current. So that's part of what you missed last time, part of what I didn't get a chance to record last time. Another thing that we talked about last time, or at least that's in the slides towards the end last time, is that if you have two wires that are next to each other, then this wire, both wires are making a magnetic field, but let's talk about this one for a second. As we talked about in that lecture, you put your thumb in the direction of the current and you curl your fingers around to get the direction of the magnetic field. So when you do that in this case, it implies that the magnetic field at this wire, due to this wire, is going to be like, you know, into the page, right? Because the way the magnetic field's going. So the magnetic field's into the page. And so we can ask the question, like, if there are moving charges over here that are experiencing a magnetic field, what would be the direction of the force in those charges? Well, if you've got a current this way, that means that the electrons are going this way, right? Electrons are going this way, the magnetic field is into the page, which means that V cross B is this way, but the force in the electrons is not V cross B, the force in the electrons is QV cross B, which means the force would be that way. And so at the end of the day, you find that the force that this wire experiences due to this magnetic field is actually towards the other wire. And if you do this whole argument over again, and you say, all right, well, this wire has a magnetic field that's doing this, so it's out of the page, and this wire is experiencing a magnetic field due to this wire, you will come to the conclusion that the force on this wire is actually towards this wire. And if you don't believe me, there's an actual video from in the last lecture that's embedded in the PDF that shows that if you take two wires and drive current through them at the same time in the same direction, they will be attracted to each other. And if you drive current in the opposite direction, same wires, but you know, the current in one is the opposite direction of the other one, it's going to drive them apart. Okay, so this is what we learned last time. I'm going to tell you right now, there's a question on the midterm that has two wires, and the currents are either parallel or anti-parallel, or maybe I tell you the direction of the electrons moving instead of the current, just to be snarky about it. And I will need you to tell me whether the force on the wires is for them to move together or to move apart. And I'm telling you right now that if the currents are parallel, they're going to move together. And if they're anti-parallel, then they move apart. Okay. This is another slide from the last lecture that, again, that I didn't get a chance to record, but the slides are there. And I like this slide because this equation is a little bit hard to visualize. So it's not too hard to look at this and say, all right, well, we've got a magnetic field here. It's going like this, that's swirling around. So it's kind of like this. So you can see the magnetic field is swirling around. That much is fine. But this equation, which is a magnetic field from a long wire, the magnetic field gets weaker with R. So the further away you are from the wire, the weaker the magnetic field is. And this image kind of codifies that, because you can see that the field lines are closer together the closer you are to the actual source of current, and further away you can see that the field lines are further apart. So I really like this because it shows you that this is a 3D thing. You know, at this point it's sort of out of the, you know, it's kind of out of the page this way, whereas this one it's down to the page. Anyway, I really like this drawing, and I like it because it shows both the direction of the magnetic field but also its strength. Alright, let's talk about some new stuff. What is this symbol? So this is what's called mu 0. It is, the constant is given by this, 4 pi times 10 to the minus 7. And I will give you that equation on the midterm. You won't have to memorize it, although it's not too hard to memorize if you wanted to. And this is referred to as mu naught. So sometimes 0 is referred to as naught. So this is mu naught. And basically, the role of this constant is that if you have some current, it's going to produce a magnetic field. The question is how strong. And so if you have some current that's here, you want to know what the magnetic field is up here. Well, space itself has properties that determine how much magnetic field you get up here based on the fact that there's a current down here. And so this thing has to do with the properties of space itself. In other words, the properties of the vacuum that determine the relationship between that current and that magnetic field. It's a little bit like that K constant for electric field. So if you have some charge, there's some number of coulombs, and then over here you want to know, all right, well, what's the electric field due to that number of coulombs down here? Well, that depends on the properties of space itself, because we know it goes as 1 over r squared, but exactly how strong is it up here? So in any case, this is a fundamental constant for the most part. Now, we use mu naught, we use mu naught in situations where you're in vacuum or you are in air. If you are in something that is not vacuum and is not air, you might be using something else, in which case you'll call that mu instead of mu naught. It turns out in aluminum we're still using mu naught, but in iron it's very different. So just be on your guard. So this is just a heads up about that. All right. So now we're going to talk about the Biot-Savart law. There is a question on the homework that's relevant to this. So listen up. It's pronounced. It's French, and so with all French words, just don't pronounce the last half of the words. So you just want to say Biot, and then like Savart. Like don't even try to pronounce the word. So I don't know, if you took French, you can try to pronounce the R. The French language has some interesting sort of nasally thing going on. But anyway, the Biot-Savart law, I think there's some slides in the last lecture that talks about it. We're going to talk about it in much more depth. I think it was extremely brief, the mention of the Biot-Savart law in the slides for the last lecture. So this is specifically the slide. This is like the only mention of the Biot-Savart law from last lecture. Should be a T there, sorry. And basically the spirit of it is that we used to think about having different charges in different places or distributions of charge, and we wanted to figure out what the electric field was. And so we would do a sum over all those charges, acknowledging that each one of them has some electric field vector that it's producing, and we would add up all those electric field vectors to produce the electric field. With currents, we are going to do something that's qualitatively similar. We're going to say, all right, well, there's a current over here, and a current over here, and a current over here. We're going to add up all those things to get the overall magnetic field from some arrangement of current. This equation probably doesn't mean much to you right now, but I'm going to give you some examples of how to apply it. And as with both of these things, often we'll see it in the integral form. So it'll turn into this. So we'll get to this in just a minute, but relax for right now. This is you'll survive. Don't worry. When I was writing this lecture in maybe 2015, there was a press release that Lockheed Martin had achieved a breakthrough in fusion research. Random fact, I'm always telling stories about Wright-Patterson Air Force Base in this class, and there's a guy who is thinking about collaborating with us at Wright-Pat who's sort of used to be at Lockheed Martin and used to work on this fusion project. So he's telling us about that a little bit last week, so that's a little bit of trivia on my end. And basically, we talked about the magnetic force, I think the last lecture or the lecture before. To achieve fusion, what you want to try to do is to use the magnetic force to confine a plasma, and you want to make that plasma as hot as you can, and eventually the plasma gets hot enough that fusion reactions start to happen. That's the short version. I'll spare you from the long version, but the point is that in order to confine that plasma, you need a very strong magnetic field. And so this device essentially has this current. There's a current moving around this thing that's creating a very strong magnetic field that we're going to use to confine plasma and to try to get it as hot as we can. And so the question is, how much current do you need to produce 4 Teslas of magnetic field? Because in the press release that I read, it said that they were using 4 Tesla magnetic fields, and this is one of the pictures from the press release. So again, our task is to try to figure out how much current this involved to produce that. Okay, so before we get into that, if there is a loop of current like this, what direction is the magnetic field in the center of that loop of current? Assuming that the current is going around this way, counterclockwise. Okay, so take a minute to think about that. Okay, so if you apply the rule that your thumb goes in the direction of the current and then your fingers curl around, then at this position in the middle, your thumb goes in the direction of the current, your fingers curl around, the magnetic field would seem to be going out of the page. Same thing up here. Again, the current is this way, my thumb's in the direction of the current, my fingers are out of the page. Same thing. I don't know if I have enough space to get over there. Down here, my fingers are going with the current like this, and then it would be going out of the page, like that. So the answer is that the magnetic field here would have to be out of the page if the current is indeed going counterclockwise. All right. Now we got to figure out what the magnitude of the magnetic field is. Now that we know the direction of it, we got to figure out what the magnitude is. So let's go ahead and do that. And we're actually going to apply the Biot-Savart law in this case. And it's not going to be as painful as it sounds. But basically what we have to do is we have to break up this loop into a bunch of tiny little pieces of current. Doesn't really matter exactly how many pieces of current, but this is what we're going to do. And so we're going to be summing over all of these things. Now, the length of each one of these pieces of current is going to be delta S, as we'll see, and all these pieces of current has a current I going through it. So already we've made an assumption that the current through this piece of current is the same as that, so on and so forth. All right, now delta S, I told you, is the length of each piece of current. And so the circumference of this circle is 2 pi r. And so if we've broken this thing up into n pieces of current, that means that delta S is going to be 2 pi r over n, right? That's going to be the little tiny length of each little chunk of current that we're considering. I think I just told you that the current indeed is the same. It would be very strange if the current here was not the same as the current here. That would imply some sort of traffic jam of electrons, things charging up, stuff like that. Alright, so the next thing is that, alright, so we're trying to figure out the magnetic field in the middle. We're using this thing to do it. This r squared is the distance from our little piece of current, our little chunk of wire, to the place that we're trying to figure out what the magnetic field is. Well, what's r squared? Well, that's pretty easy because that's just big R squared. That's just the radius of the circle squared. So this crazy looking thing turns into 4 pi big R squared, where, you know, big R is this radius here, okay? So we've taken, so already this looks a lot more manageable. There's still this scary thing going on, but we'll deal with that in a second. Now, the next thing is that this is a cross product. This is a cross product, and so you've got, remember when there's a cross product, we can use our our right-hand rule. So if there's a cross product, there's this thing, and then r hat is always in the direction of wherever it is that you're trying to calculate where the magnetic field is. So if I have a little piece of current here, it's pointing in this direction, and the magnetic field that we're ultimately trying to get is in the middle of this circle, which means that the cross product, which always has to be perpendicular to either one of those things, is going to be perpendicular to both of those, so it's going to be out of the page. So that's why we get this z hat over here. So again, I've turned this crazy looking thing into a z hat, and then I have a sum over each little length of each wire. This part is actually pretty simple, because we know that the length of each chunk of wire is 2 pi r over n. And so if you sum up all those things, all those little chunks of wire, 2 pi r over n times n, you're just going to get 2 pi r over n times n just gives you 2 pi r, right? So this is what I was saying before, is that the wire is sort of pointing this way, the r hat is pointing towards the magnetic field. You get a cross product, you get a z hat. I suppose you could say this is a k hat, based on the notation we did in Physics 1250, but in any case, it's out of the page. And then there's some cancellations that happen, the pi cancels, stuff like that. So anyways, the magnetic field you get in the center of this thing is mu naught I divided by 2r. And so if you increase the current, you get a larger magnetic field at the center. You make the radius smaller, you get the larger magnetic field at the center, so on and so forth. So anyway, the Biot-Savart law turns into this relatively straightforward thing. So now what we can do is we can take this relation and we can say, well, according to the press release, they got 4 Tesla of magnetic field at the center of this loop. And from the picture, at least, it looks like the radius is maybe 30 centimeters. And so you can actually solve for the current that would be required to create a 4 Teslas of current. And if you run the numbers on that, you will find that the current is 2 mega amps, 2 times 10 to the 6 amps, which is crazy large even for like advanced magnet systems. It's just kind of crazy. So something's missing here. This is not actually how they actually do it. 2 mega amps, by the way, is the largest current that I'm aware of that humankind have been able to create. So probably not what they're doing in this project. And you know, the one project that can do this much mega amps can only do it for like 20 nanoseconds that I'm aware of. Anyway, so this is nice, but it's not going to explain our 4 Tesla magnetic field. The answer turns out to be that we've been doing all this assuming only one wire wrap. But there's one wire that has some gigantic current, and that is the thing that produces the magnetic field at the center. In reality, you have many wraps of wire around and around and around, and you can imagine from that picture that inside of that coil there's many wire wraps. And so when you do that, according to Biot-Savart law, well, there's all of those pieces of current contribute to the magnetic field at the center. And so you can add up all those things, and you find that this is multiplied by the number of wraps. And so when you do that, depending on what you assume, if you assume 100 wraps, now you're getting a current of a few hundred amps, maybe a kiloamp, and it's the kind of current that maybe like a kilovolt potential could potentially apply. So all of a sudden it's something that's not insane to try to produce in the laboratory. So I'll go ahead and resolve the mystery there. Now when you have current like this in a loop, the 3-dimensional view of it is a little bit like this. This isn't perfect because it's sort of like a 2-dimensional cross-section, but it's a little bit like this, right? So the current is sort of thumb in the direction of the current. So the magnetic field is sort of swirling around this way, whereas over here, the magnetic field is sort of doing this. I'm putting my thumb in the direction of the current. The magnetic field is kind of swirling around this way. and then in the middle of the magnetic field is straight up. So that's what that would look like in terms of magnetic field strengths. Alright. So I think we're going on to the next topic. So this is the magnetic field of infinite wire. We already talked about this. The next part, what we're going to do is we're going to use the Biot-Savart law to calculate the magnetic field from a finite wire. And the reason that this is a useful thing to do is because we don't always have wire loops that are made of circles. Sometimes we have triangles, sometimes we have squares, maybe we have pentagons, I don't know. But we want to know what is the magnetic field at the center of that pentagon, at the center of that triangle, at the center of that square. And to do that, if we just can figure out what the magnetic field is sort of in the middle of a finite wire, then we'll be able to do those calculations. And I'll show you how to do those calculations in just a minute. Now before we jump into this and apply the Biot-Savart law to this, I do admit that this is a strange example because you have this current that's sort of starting from nothing and going this way. And if this is a real current, you'd end up finding that this end gets positively charged and this end gets negatively charged. So don't worry about that for now, because eventually we're going to sort of figure out what the magnetic field from a finite wire is, and then we're going to sort of assume that there's some other wire that connects with this thing until it eventually makes an actual loop. So I agree with you, this is kind of it's an odd thing to do, but it'll work out in the end. Before we start, bear in mind that this distance I'm going to call A. I think I'm doing this because the book often uses A for that, so it's not an acceleration, it's just this is the distance from the middle of the wire that we're trying to figure out what the magnetic field is. Alright, here we go. I can't guarantee this is, the chapter number might have changed, it might be chapter 29, I'm not sure. Anyway, so our goal, and what the Biot-Savart law is good at, is that it takes each little chunk of wire, right? So we're going to break this up into a bunch of little chunks, n little chunks. And what we're trying to figure out is what is the contribution to the magnetic field here as a result of the current that is here. And that's what the Biot-Savart is good at. So we're going to sum up all these little contributions, and these are given by this crazy looking formula. Okay? So it's going to be a little bit trickier than last time, but we'll get through it together. So, alright, so when we do this, the r hat, remember the r hat is always pointing in the direction of where you're trying to figure out what the magnetic field is. Okay? This is the distance from the magnetic field that you want to the little chunk of wire that you're dealing with. So something that's going to be different about this case is that the distance from our little chunk of wire to the point where the magnetic field that we're trying to estimate is no longer just going to be a constant like it was for the circle. It's going to depend on exactly where we are along here. So we have to be mindful of that. We can manage that because we can just do we can use Pythagorean theorem. We can manage that. We can use Pythagorean theorem and realize that if this is x equals 0 here, and this is like x or minus x or something like that, then this Pythagorean theorem tells us that r is equal to the square root of x squared plus a squared. Okay, so we know that's true. We know Pythagorean theorem. So what we can actually do is replace this r squared with basically x squared plus a squared. So that's what we're going to do down here. So it's not looking horrible just yet. The next thing we're going to do is, I think we're going to work on the r hat and the delta s. So remember that the r hat is always pointing in the direction where you want to know the magnetic field. In this case, there's the r hat, there's the s hat. The tricky part is that they're not parallel to each other. They're not in the same direction, but they're also not completely perpendicular to each other. There's some angle between the two. And if you do the vector arithmetic with the cross product, this is basically how it works. You're saying that delta S is only in the x hat direction. Suppose in the notation of physics 1250 would say this is I hat, but whatever. So delta S is only in the x direction. But r hat is a little bit in the x direction and it's a little bit in the y direction. And so when you do the cross product, you sort of cross multiply all this stuff. And it turns out that the cross product of x hat with x hat is going to be 0, because remember, the cross product is the smallest when the two things are in pointing the same direction. So x hat is definitely pointing the same direction as x hat. So this is going to go to 0. But x hat and y hat, those are perpendicular, so this is not going to go to 0. And in fact, this is going to become z hat. So this crazy looking thing becomes delta s cosine theta. Maybe there's another way of arriving at this conclusion. This is the way that I think about it. But anyway, this is what you get. And this theta is the theta here. And theta depends on exactly which chunk of current that we're talking about. So what we can do is we can replace this thing with the delta s cosine theta. So we end up with that. Now we're going to do one more clever thing, which is that has to do with this cosine theta. So we need cosine theta, but there's this r squared, there's a squared. The thing about it is that cosine theta, again, this is the angle. Cosine is adjacent over hypotenuse. So adjacent is a, the hypotenuse is square root of x squared plus a squared. That means that we can replace this cosine theta with a over the square root of x squared plus a squared. The other clever thing we can do is say, well, delta x is in the x direction, so let's just replace delta x with delta x. And we end up with this thing. So do you see how the square root here times this thing gives you a 3/2 there, and then there's an a. I promised you that there was an a, so there's an a down there. So alright, so we've gotten it pretty far now. The last step is the part where we have to appreciate that this is not the only chunk of current in this line. There's a whole bunch of currents, and there's a whole bunch of contributions to the magnetic field that's here. And so you need to sum up all these things. And so basically we need to sort of stare intently into this equation, maybe avert our eyes, gaze off into the distance, squint. I don't know if you guys have ever done magic eye. You sort of look through the page, and so if you do that, you'll find that this becomes this. All right, so the a goes out front right there. You've got a dx here. This goes in the bottom, and you end up with this integral. So let's talk about this integral on the next page here. By the way, this integral goes from negative L over 2, right? Because the smallest that x can be is negative L over 2. Or the most negative that x can be is negative L over 2. The most positive x can be is positive L over 2. So this is what you get. And I could probably do this from memory on a piece of paper if I had to, but I can also just go to Wolfram alpha and do the same thing. So this is what I get from Wolfram alpha. And so when I put in those two limits, L over 2 minus L over 2, I'm getting this thing minus a negative thing. So the minus times the minus makes a positive, and we end up with this thing. Okay. And by the way, I still need to multiply by this stuff, so sort of drop that for the moment just for simplicity. So I'm only evaluating the integral right now. We end up getting this. There's one more thing, there's one more clever thing that I can do here that I would not be clever enough to think of if somebody else hadn't thought of it for me, which is that we can multiply and divide by 2 and convert this into this. So L over 2, and then so I'm multiplying and dividing by 2. So when I do that, right, so I'm multiplying this by 2 and dividing by 2. So 2 over 4 is 2, and so I end up with this thing. Now, why was that a clever thing to do? It's because if you stare at the diagram for long enough, you realize that this thing over here is actually sine theta. So which is kind of clever. And so at the end of the day, you end up with this is the magnetic field at that spot that's in the middle right here. You end up with sine theta there. So you end up with something that's, you know, relatively concise formula, which is kind of nice. So this is the formula that I get as long as I situate the magnetic field sort of halfway along the wire. In the book, yeah, I'll talk about what they do in the book. So one thing to notice here is that if theta is bigger and bigger, and as it gets closer to 90 degrees would be a wire that's infinitely long. And so sine of 90 is 1, and so if the wire is infinitely long, you get mu naught I over 2 pi a, and you basically get exactly the same formula that you would with the finite wire. So that's kind of a nice result. So that tells us we probably didn't screw anything up when we did this. Okay? So that's a nice little check. Alright. Now in the book, I don't know if this is equation 30, it might be equation 29.1. Anyway, there's an equation in the book that looks like this. I personally find this equation to be very confusing, and this equation was arrived at not assuming that the magnetic field was in the middle of the wire, but assuming the magnetic field might be anywhere, anywhere between the ends of the wire. Again, a finite wire. So it's a similar problem but different, and so they find this to be true. Whereas, we find this to be true. To me, the annoying thing about this result is that one of these angles have to be negative. And it's not obvious that it would be negative. So if I was deriving this, I would say sine theta 1 plus sine theta 2. So that both these angles could be positive, because in the diagram they certainly look very positive. But actually they are defining one of these angles to be negative. And so if you do that and you say that, all right, well, if theta 1 is equal to minus theta 2, and you stick that into here, well then minus theta 1, the sign of that is negative sine, negative gives you a positive. You end up with this thing. 2 over 4 gives you this thing. So their result agrees with our result as long as you assume that one of these two angles is negative. So anyway, you heard it here first. I think this is about all you need to do the worksheet and things like that. There might be a question on the homework that might be better to use for this. I'm not sure. All right, so those two are consistent. So far, part of the idea of the Biot-Savart law is that magnetic fields are adding like vectors. So each little chunk of wire has a magnetic field it produces, and all those magnetic fields add together at the point that we're interested in. So this is also true of magnetic fields. So a type of problem that you will see, and a problem that is on the worksheet for today, is basically find the magnetic field at this point, assuming that this current is 2 amps and that current is 2 amps, and assume that it's a long wire. So you can use the infinite wire formula, and so with a question like this, you say, all right, well, current is up like this, so the magnetic field here is actually going into the page from this wire. However, there's a current over here that's down. If I wrap my fingers around, the magnetic field would be out of the page from this one. And these two things act against each other, and you have to figure out what is what is the resultant magnetic field out here. Interestingly, in between these wires, the magnetic field from this one would be out of the page, right? So current's this way, magnetic field's out of the page. Over here, the current is down. Sorry, current is down, but this would also be out of the page. So that the magnetic field from this one. So you don't necessarily subtract them from each other in the middle. You add them together, but over here you'd have to subtract them from each other. So this is one example of a kind of problem that we will ask you. This is definitely on the midterm. I think it's on the final. So be on your guard about these types of questions. Now with finite wires, so I promised you that we were going to use the finite wire formula and apply it to a wire loop of a particular shape. Well, we can use that formula here, where the length of this thing is like so. There's 4 pieces of wire, so you have a factor of 4 here. They all have the same current going through them. It's not too hard to figure out what the distance from the magnetic field is. The tricky part, I think, is sine theta, and because theta is just, it's not this full opening angle, it's just half of it. So you have to figure out that in this case the theta is 45 degrees. So sine of 45 degrees is 1 over square root of 2, and so this is what you get for the magnetic field at the center of the thing. You do the same thing for triangles. I think there's different examples on the worksheet. Okay, now before we get to the worksheet, just sort of a fun thing to talk about are what's referred to as brushless DC motors. Now this video is actually a brushed DC motor, and sometimes I hear about this so that because like at Lowe's there are hand drills where some of them are brushed hand drills like this one, or you can pay a little bit more money for the brushless hand drill. What's the difference between that? Well, brushed means that if you look closely at this thing, you'll see that there's an electrical connection here with this metal, and as soon as the metal leaves that wire, it stops, and the people that made this motor are cleverly taking advantage of the fact that the thing is rotating to push the current in different directions in this thing. And as they push the current in different directions, it produces a different force. So the force here, due to the current, is up. But then the current switches and the force is actually down. So this is what's referred to as a brushed DC motor. But for a lot of applications, this is a fundamentally bad idea. Can you think of a reason why this would be a bad idea? I'll give you a hint. It's particularly in cases where the RPMs are very high. So for example, my electric car, if you tried to use a motor like this in my electric car does not have a transmission. That's part of why I love electric cars. Teslas have transmissions because they're weird, but there's one fewer thing to break on my electric car because it doesn't have a transmission. And so what it does have is it has this axle in it that has a bunch of permanent magnets on it, and we can use that to drive it up to high speed. If something like this were used in a car like mine, remember that there's no transmission, which means there's no gears. So when I'm going down the highway at 70 or 75 miles an hour, I'm still in the first gear. And so this thing would have to be rotating at thousands of RPM to travel on the highway. If that happened, it would get very hot, and eventually the material would get worn down. And so for anything that has a really high RPM, brushed DC motors are not going to be your friend. But thankfully there's a solution called brushless DC motors that is like this. So this is a nice little animation. And the point here is that there's no physical connection. There's nothing that's like rotating and rubbing against a wire as this thing goes. Electronically, we are applying different currents and different coils to try to get this bar magnet to move around, essentially. So let me start that over again. So initially the bar magnet is here, and then because we have a current through C, then we switch it so the current is through B, and then we switch it again so the current is through A. And as we do that, that causes the bar magnet to rotate. In other words, it causes a torque. The torque produces the motion, and this is the basis of brushless DC motors. Now you might see motors that have many more coils than this. Maybe it's like 16 coils or something like this. This one has 6. But this is the basic idea, and the reason they call it a DC motor is because the current is always constant somewhere. It switches from being constant here to constant here to constant here to constant here. The current never really switches off; it just switches coils, so to speak. So this is a nice way of doing it. It's a nice application of magnetic torque, which I talked about earlier here. All right. Now, I know I just introduced Biot-Savart law, but hopefully by this point you've appreciated that it can be complicated to apply. Is there any sort of slick way of avoiding doing a full Biot-Savart calculation? So this reminds me a little bit when we were talking about electric fields and we calculated the electric field from like 2 or 3 charges, and it was kind of a pain. And we started to wonder, is there any faster way of doing this? And so let's ask that question not of electric fields but magnetic fields. The answer is yes, and the answer is something called Ampere's law, which is this crazy looking thing. So hold on tight, this is not as scary as it looks. So this is an integral. S is some kind of a path. This is a path integral because it has a circle in it. So it's an integral. So integrals that don't have circles in it go from one point to another. Integrals that have a circle in it are either doing a closed surface or it's doing a path. In this case, we're not integrating over an area, so it's not a closed surface. Instead, we're just integrating over some sort of a line. And so this circle means that we're gonna end up where we started. You notice there's a dot product between the magnetic field and this thing, and that'll become important in a second. And so let's use this thing to figure out what we already know, which is the magnetic field from an infinite wire. Okay, so here's this thing. So the magnetic field is kind of swirling around this way, and so if we draw a path here, again, there's not necessarily current going through this path. Let's just say that there's a path, and we go around that path and we integrate the magnetic field dotted with this little path. Well, the magnetic field on this path is in the same direction as this little as we're going around the path, as the ds there. And so if they're parallel, that means the dot product, which has a cosine theta, well, the theta is 0, so the cosine is going to be equal to 1. And so we can actually go ahead and get rid of this dot product and make it like this. Now we know that because we're equidistant from the wire, that the magnetic field has to be the same magnitude. So we can take that outside of this thing. And now the only thing we have to do is integrate over these little tiny pieces of path, which in total will add up to just the circumference of the circle, so 2 pi r. In this case, 2 pi a, because a is the distance from the center of the wire. So that's what we get. And so we can solve for the magnetic field because this thing is equal to mu naught I. So we can do that, and we find that indeed the magnetic field is mu naught I over 2 pi a, like we had before. So it'd be very strange if you got something different, right? So this is a viable way of coming up with this. Okay, so that's fine. In general, you can use it in more general cases. For example, with cylinders of wire, and there's a current going this way and a current going that way. Or instead of having we're basically been treating it as a thin wire, but we might have like a thick wire, and we want to know what the magnetic field is inside of that thick wire. Now, what's important for those applications that we're going to go through, what's important is that the current here is the current through this loop, right? So there's a loop here that we're doing. Important thing is that the current here is the current through that loop. And so if the current is going up, then the current is adding. If the current's going down, the current's going the other way. Maybe it's subtracting. So sometimes I like to write this as I through, and I think even on the equation sheet it says I through, because it's the current that's going through that loop. So in the next lecture, I'll give you more examples of how to apply Ampere's law to different problems. But that's all you need to know right now. I just want to introduce the idea of it.